Well, I don't know about you, but I think it's time for a kit build, and this is the one I've chosen to do today. It arrived a couple of days ago, and there's a screen there, an LCD, and a PCB, a fair few resistors, and some hardware crystal in there, and an Atmel ATMega16, and this is a function generator based around this ATmega. So if you forget about the screen for a minute, there's actually only two active components on here, the ATmega16 and an LM358 dual op amp. Everything else is just capacitors, potentiometers, and quite a lot of resistors. So I'm going to solder them in straight away. So soldering job number one is all these 20k resistors here, which all go to these last 8 pins on the ATmega. They go straight through, if I can do that without them all falling out. There we can see 8 resistors going straight to those 8 pins. It's a nice through-hole plated board this, and nice and clean as well, so no additional flux required, just the flux in my solder here. And now with those 20k resistors soldered in to those 8 pins there on the ATmega, I'm going to do these, of which there are 3, 6, 7 10k's and a 20k. So what are all these resistors about? Well, remember, the ATmega is a digital device, and we're looking to make waveforms display on an oscilloscope or what have you, and this is an R2R resistor ladder, and I guess it could be described as a crude digital to analog converter, although depending on how you design it, it's not always that crude. But essentially it's a series of voltage dividers which can create various voltages on the output by switching on different combinations of the digital outputs here of the ATmega16. So if we take a look at this Wikipedia article about the R2R resistor ladder network, we see this diagram here. And I'm not going to go into this in depth because there's a lot of better videos out there than I could explain, and it's probably a video all by itself. But essentially we've got a series of voltage dividers all connected together. If we put 5 volts here on this digital output, well, the voltage divider here, if we ignore the rest of the circuit, will produce a 2.5 volt output here, because on this rung of the ladder, the very bottom rung, it's 2R and 2R. So we'd have that voltage. And by turning on various different digital outputs, at the output here, we can get various different voltages in quite small steps. So this R2R resistor network ladder here is an 8-bit resistor ladder, because that's using 8 digital outputs here on the ATmega16. So it's able to increment in 256 steps, a minimum of 19.5 millivolts, all the way up to 4.98 volts, just 19.5 millivolts in fact, from 5 volts. Now, as you can see, I've gone ahead and done most of the soldering now, but before I put the chip holder in here for the LM358, the op amp, I just wanted to have a quick look at the tracks here. And this op amp is here simply to change the amplitude of the signal and the offset, the DC offset. And to be able to do the latter, it needs a 12 volt positive and a 12 volt negative rail, which you can see these tracks go straight to the LM358 there, to the positive input and to the negative input there in the top right, pins 4 and pins 8. And you'll remember I built a split rail power supply a couple of weeks ago, and this is it. And it was really interesting to see Julian Eilert's video last week on this same kit build, because he did a bit more research and found that the SEPIC power supply application circuit diagram I showed from the XL Semi XL6008 datasheet, which is the switch mode power supply that gives the positive and negative rails to these linear power supplies, which are now hidden under heat sinks. And he found out XL Semi hadn't really acknowledged the work of Slobodan Chuk for the conception of the Chuk negative converter, which gives the initial negative rails in this particular power supply. And while we're talking about acknowledgements, this function generator circuit design seems to be designed by the person behind scienceprog.com. Hopefully I've got that right, and that is the designer, and their post on scienceprog.com goes back to 2008. And it does seem now there's quite a few of these kits on eBay where the manufacturers have found the circuit and the code, in this case for the microcontroller, and are selling kits, which, to be honest, is great, because this is a really good, nicely built kit. For, I think it was £7 I paid for it. But it is nice to acknowledge the work of the original designer. So that is it complete. I just need to put the microprocessor in now, and hopefully neither of these have suffered from being in this polystyrene, which I'm pretty sure is not anti-static. All the legs are in reasonable condition, but those legs do need rolling back a little bit. And hopefully now that will squeeze in quite nicely, and the LM358 will do the same. Okay, so I've got my 5 volts there on the purple, plus 12 volts on grey, minus 12 volts on white, and black is ground. Remember, this will take anything from 5 to 24 volts on the input, so good luck everybody. Well, the screen has lit up, but there is no data on it at the moment. Perhaps I need to adjust the screen. There we go, we've got NE. NE. What does NE mean? Let's reboot it now that we know we've got the screen. See what happens. Oh, there we go. Sine 0 megahertz. So this screen, sadly not doing the right thing, is it? Let me check a few connections. Okay, so a considerable amount of time has passed. In fact, it's been a week since I was last looking at this project. I have replaced the screen because I had a spare one, and unfortunately that's made no difference. If I just reboot this, sometimes it shows roughly the right thing, but more often than not it's complete madness. And I have also, let me just unplug that, replaced the 22 picofarad capacitors, which are under the ATMega16. The crystal seems alright, and there's nothing else supporting this ATMega16, so I can only assume that it's actually the ATMega which is at fault. And if you remember, it did arrive on a piece of polystyrene, so perhaps that is part of the issue. So as a result, I've gone out and I've bought another kit, the same one, for spare parts essentially, and straight away I've noticed an issue. Right, so in here there's all the, well, the majority of the components, and that's fine. My concern is around the fact that this ATMega has no pin protection on whatsoever, and now has a number of bent pins, and the chip carriers fared even worse, I'm afraid. But as long as I can straighten those out, I hope this chip will be alright. Well, I think I've managed to straighten them out enough. Now, of course, I could have just bought another ATMega16, The code is freely available, and I believe it's on scienceprog.com, the original designer, I believe, of this circuit. But actually getting hold of a whole kit was quicker and, well, not cheaper, sadly. So I've eased the original ATmega there. I've just marked with a small black line, and hopefully this will fit in. I'm going to be really careful, a bit gingerly press that in, because these pins will definitely be a bit weak now. And if we get I'll get the original screen here, plug that in, find my 5-volt rail there on purple, ground on black, and plug my dual power supply. There we go, we're not seeing anything, and that's because I've swapped screens and we may need to adjust the contrast. Or it could be that it's got nothing to show me. Oh dear. Okay, so my bench is a bit of a mess now, but I've basically built this second kit here, installed all the components here to get the screen and the ATmega16 up and running. So let's plug it in. So that's the original one, which I think is broken. Here's the newer one, which actually did less than the broken one in the other. That's the screen I need. Okay, the other end is plugged in, and this screen is green. The last one was blue, but I don't care what colour it is, as long as it works. And it does. So now that we know that this minimalist circuit works, I do want to know if the original ATmega16 is going to work in this circuit. So let's get my... And yes, it does. So what is wrong with the original build here? Now, the only component that I didn't swap in this area was the crystal. So is the crystal on this board damaged? Is that the problem? Is it resonating at different frequencies? Is it not consistent? So is it the crystal here that's at fault? I wonder if I've got any more 16 meg crystals. Well, luckily, being a sucker for a bargain on eBay, I've got plenty of 16 meg crystals here, so I'm going to try and chop that one out and replace it. So the old crystal's been removed. I've used some desoldering braid to tidy up, and apart from the fact that my iron caught the edge of this holder, I think we should be good to go. So let's get one of the ATmega16s, because we know they both work. Plug that in there. Find a screen that's going to work on these pins. And again, that looks like nothing is happening. Well, at least we know it wasn't the crystal. So what else can I do apart from keep adding components and testing as I go along? I can't imagine that the R2R resistor ladder network is going to cause any problems, so I'll add that next. So with the R2R resistor network in place, yep, still working fine. Now the next thing I'm going to look at is the switches, and they only fit into the PCB one way. And if we check the tracks here, one side of the button here goes to the ATmega16 and the other side here goes to ground. So I am just going to probe those and check that that switch is orientated the right way. So with one switch here in place but not soldered, no contact, but if I press down on the PCB, apply some pressure, that's definitely working. So that definitely seems to be the right way around. So I've now installed these two resistors here, which are 100k, but they're really to do with the amplification circuit of the LM358, so I can't imagine. No, they don't cause any problems. And adding the LM358 doesn't cause any problems either. I am starting to wonder if this is the way forward for kit build videos, doing everything twice. So these two resistors down here, again a part of the amplification and offset LM358 circuit, but yes, they're absolutely fine. And finally the potentiometers, and I'm sure this will be all fine. There we are. Much more time has passed, so I guess this in a way is part 3, but unfortunately this original function generator circuit is still not working. The screen shows gobbledygook half of the time, and unfortunately I've tested and probed and I can't work out what's wrong with it. So hopefully somebody will notice in the video when I publish this, if I ever do, that I made a glaringly obvious mistake early on. Otherwise I can only put it down to gremlins. However, the second one is working, but you'll notice I haven't put the BNC connections on here. Instead I've put a couple of bits of wire so I can easily probe it on my oscilloscope. So let's plug it in and see what it does. So I've got the oscilloscope connected up now, and everything should be just about in shot. The function generator down here and the dual PSU here, and if I plug that in, we've got a lot of noise, and we can see just about it's saying sine 100 Hertz, and if I turn that on, well, that doesn't look like a sine wave, does it? That just looks like a lot of noise. And interestingly, the LED on the dual row power supply is also going on and off and looks quite dim. And those 12 volt regulators, oh yeah, that's getting pretty hot pretty quickly. Oh, more trouble. Now, as we discussed earlier, the only thing using those plus 12 and minus 12 rails is the op amp. So I'm wondering if that's got an issue as well. Let's swap it out for the spare one. So before I do swap the LM358, I'm going to power the op amp with 24 volts from my converter here to see how much current it was pulling, because that regulator got very hot very quickly. And yeah, if I give, well, it's at 40 milliamps there, the voltage can't raise up. It's consuming an awful lot of current, so I'm pretty sure it's the op amp that's at fault. So op amp shouldn't take any current really whatsoever. So with that one replaced, let's plug in the power supply again. I've got two bright LEDs and a bit of noise there on the oscilloscope. We've got a sine wave here, 1000 Hertz. Let's turn it on, and that seems to be doing what we'd expect. There we have a wave. It's being clipped slightly there. That's better. That must be the attenuation, I think. But that's definitely a sine wave. It's not perfect. There are some anomalies. It does seem ever so slightly noisy. And the frequency showing on my O1 oscilloscope here is exactly 1 kilohertz, so that's not too bad. Can we adjust it? No, we have to turn it off. That's the wrong way. Increase on the right hand side. So if I give it a 10 kilohertz sine wave, switch that on. Again, this agrees, 10 kilohertz. Excellent. I've adjusted the light slightly to hopefully reduce the glare on the screen. It's not perfect though, I'm afraid, but this power supply now seems perfectly happy. They're not warm at all, so we'll stop that. The screen does do some slightly funky things. Let's press up. No, we're not going to go to the high speed yet. If we look at a square wave at 10 kilohertz, and zoom in there. It's not perfectly square, is it? It does take a little bit of time to rise up, but that's understandable. 10 kilohertz. We also can create triangle. There we go. Sawtooth. Very good. Reverse sawtooth. And ECG. There seem to be some spurious signals on there. So what's next in the menu system here? We can change the frequency steps. That's quite handy. So you can get up to higher frequencies more quickly. Press enter on there. Oh no, we'll leave it at 1000, I think. ECG again. Noise, we can create some random noise. So if I zoom out, it looks reasonably random, but it's just a bunch of square waves. So 65.5 kilohertz seems to be the fastest we can go for a sine wave, and there it is. It's a bit shaky at that point, and presumably all the other waves are the same. Yeah, can't increase that any further. 65.5 kilohertz. That is, of course, apart from the high speed output, which is square only, and the attenuation is a fair bit lower, and that's because that's directly from a pin of the ATmega. So that's a 1 megahertz output there, and that's confirmed by the O1. Now I was just trying an 8 megahertz high speed output, and as you can see, the screen's gone a bit crazy again. And actually the output, the square output here, is 1.295 kilohertz. Well, I have to say this is one of the most frustrating kit builds I've ever done. Can I get that first function generator to work? Can I heck? The second one arrived and it had its own problems. All the pins were bent on the ATmega. It's still showing some spurious information on the screen every now and again. And the op amp was faulty. In fact, it almost blew up my dual rail power supply. So I can't really recommend this as a function generator, but if you do want to go out and buy one, well, perhaps you want to buy two. And consider, you know, booking out at least a couple of days of your free time. If you got to this point in the video, I really appreciate you getting all the way to the end. Hopefully you enjoyed it if you did. Your comments are welcome down below, and I'll see you next time. Thanks for watching.